So without further ado, today's presentation is on machine learning in the extractive industry, the potential opportunities, challenges, and threats. Machine learning is one of those buzzwords that everyone seems to hear these days and could potentially revolutionize certain industries for better or for worse. However, one does not hear much about the extractive industry, which is where we are luckily having Alexey step in. I'm very pleased to introduce Alexey Cherkaev. He has completed his MSc in applied mathematics at Moscow State University. He conducted research on Lorentz variant Hamiltonian systems with constraints. He switched to engineering and both MSc and PhD in chemical engineering, which focused on heap leaching modeling. Alexey also conducted research on the application of machine learning methods to mineral processing operations. Currently, he is conducting research on machine learning methods in pyrometallurgy. It seems that I might have broken up slightly, so I'm going to hopefully be heard when I say, welcome, Alexey, over to you. Alexey, can you hear me?
Yes.
Okay, thank you so much.
Okay, now let's hope that it will work again. Begin. Right, can just somebody confirm that you see the presentation?
Yes, I can see it.
Okay. Thank you, Aysha, for introduction. So let me just go straight in. So I'm going to go a little bit about what machine learning is about. I'm just going to leave a little bit of the history as well. And I'm going to show some example in industrial application. For opportunities, challenges, and threats, well, I hope we'll have some good discussion about it. Okay. So the whole this machine learning business, it's all started long time ago. At the time, it was still called cybernetics. Now, if you ever watched that movie about Alan Turing making a machine that breaks Enigma code, that was basically the beginning of it. And at some point, it split to something what we call today computer science, or maybe it used to be called electrical engineering to some extent. And that deals mainly with just programming, informational systems, and so on. And out of it branched out the area that's called artificial intelligence. So, and there were some early applications of artificial intelligence as early as, I would say, 1960s. Okay, and eventually it evolved to what we know today as machine learning. We can say that machine learning is a part of artificial intelligence. Now, the history of artificial intelligence is actually quite interesting. The early applications there and the early methods, they were essentially what we call the pattern matching, where you have certain patterns, you have some inputs, and you try to match them according to a particular shape, and you just apply some simple transformation rules. Now, there was interesting, I can't remember exact now dates, I think it was late 1960s, maybe early 1970s, they developed the first chatbots, but very primitive ones. Okay, and there was one that's called Aysha. Aysha was mimicking sort of a psychoanalyst when you chat to it, I guess. And another one was Perry. The Perry was mimicking a paranoidal behavior. Fun stuff happens when you make them chat to each other. So I'm just going to read quickly through what it says on the slide. Perry, I don't understand your motives. Aysha, why don't you understand my motives? Perry, shouldn't I be? Aysha, why do you say that just now? Perry, that's just the way it is. Aysha, suppose it's just the way it were not. Perry, so? Aysha, I'm not sure I understand you fully. Perry, you harp on the same question too much. Aysha, what does the similarity suggest to you? Perry, I don't get you. Aysha, do you wish that you did get I? Okay, there is some message in the chat, but unfortunately I cannot see it. Anyway, so as you can see that getting those, getting them chatting to each other kind of devolves very quickly and degrades rather quickly without proper intelligent human input. Now, the early applications were not all that bad. Some useful stuff came out of it. In particularly successful was symbolic mathematics, and such as computer algebra systems such as Maxima or Mathematica, or early game engines like the chess engines. They were not as good as the ones that you would have today, but nonetheless they were pretty good. The problem that came with early artificial intelligence application was that all those patterns and all the transformations that you want to do on those patterns, everything had to be done by hand. And it worked okay in a closed domains, such as mathematics. But if you open it to some more open problems, those patterns is just a number of those patterns that you need to recognize, and the kind of transformations that you need to perform on them just becomes too large. And by about mid-1980s, that realization settled in, and late 1980s, early 1990s, artificial intelligence was barely breathing. And then came what we call machine learning. And that came with most important thing, and that was data. There was tons of data. There was sensors that were installed, the data was collected, there was internet that was allowed to transmission of the data. And now, instead of hand designing all those patterns and transformations, what you could do now is allow the data to sort of dictate it by itself. Okay, can I just make a quick check-in that everybody still can hear me?
Yes, we can hear you perfectly, Alexey.
Okay, perfect, thank you. Otherwise, it's a little bit like talking to the void.
Sorry about that. No, I know it is always a little bit, I always require some feedback. Just like a little giggle would be great every now and then, but it doesn't work.
Yes, that
like
will be perfect, yes.
Yeah, no, sorry.
All right. Okay, so now let me go back. Here we go. So now if we compare the classical artificial intelligence and what is offered by the machine learning, we see that the classical ones, you had handwritten patterns, whereas in machine learning, patterns are discovered in data, and you can sort of, I don't say dictate, you can sort of guide it what kind of patterns it would discover, or you can let the data speak for itself completely. The classical AI has very nice advantage, though, in the sense that it's absolutely precise. Whereas in the machine learning, the result that you get is probabilistic in nature. So you are heavily relying on certain statistics and you never get it 100% sure. And also in classical AI, you can always query the system, why it arrived at a certain answer. Whereas in machine learning, that could be a very, very hard task, and often you can't track at all where the answer came from. It just came about. Right, so why actually we want to do it anyway, and especially in the industry, right? I mean, you may be familiar with the use of machine learning in something like marketing and advertising, but in industry, why do we care actually? So if you have a plant of reasonable complexity, and you can have different tasks. You can ask yourself about designing it. You can ask yourself about how you operate it. And in order to answer those questions, you can start from rather fundamental things, which generally come with quite a nasty differential equations with parameters and so on in it. The problem, however, is that those equations to formulate for the units, they are often very hard. So you have, well, for example, here you have a sag mill here. Well, try to write the equation that would describe the grinding of the mill. That would be quite a challenge. Secondly, you might get the parameters in those equations, which might be fundamentally correct, but you might find yourself that you need parameters that no way you can actually find them. So the alternative to that would be the approach where instead of trying to get absolutely fundamental understanding and fundamental way of formulating the process, well, you collect a hell lot of data out of it. All right. Depending on the processing industry, now we're talking about extractive metallurgy, it might be easier or more difficult to do. We can discuss about it that a bit later, but nonetheless. So if you have a data, and now can you find something in that data? Can you find certain answers, such as, is there a fault somewhere in the system? For example, you can look at this top graph here, and there's some oscillations happening. That can be indication of a fault on some controller. Or am I operating at optimal conditions? Did I shift my operation from where I was actually at which it was supposed to operate it, in which it was designed it, and so on. So that's the idea of the machine learning. So we want to try to bypass the fundamentals, which can be very, very hard to get, and rather look at the data. Now, this is a little like very simplified sort of classification, if you want, of what the machine learning really is about. So on the left column, we call the supervised learning. And there are two typical tasks there. The one task called regression. Regression is when you have a certain output, okay, and this output is continuous. So, for instance, you want to figure out from your data the composition of your tailings, right? So then that composition, in whichever form it is, weight percentage or molar concentration or whatever, that would be your output, and that output is continuous. In that case, you have some predictors, some other things that you can measure easily, and you try to find the regression form to get this output. Classification, very similar idea, except that your output now is not continuous. We call it categorical, so it's discrete. It may be 2 values, maybe 3 values. The task is similar. Now you just need to classify your output to one class or another. On the right side, what we call unsupervised learning. Now this is rather quite a bit more challenging task. And that is when you don't know what your even output is, and you're trying to discover it in the data. The typical tasks there include noise removal and what also we call the feature extraction. That essentially comes down to simplifying the data, and that's again, it's when your data is continuous. Now in a picture here, you see it's sort of a projection of lots of points into the plane and from the high dimensional space. That's very kind of typical task of this unsupervised learning. And again, if we're dealing with not with continuous variables, but with some kind of discretization of it, we can try to cluster the data. So instead of having the whole ensemble of different data points and observations that we have, we try to say, okay, can we actually describe our data with much simpler way? And the picture here, just with those 3 points. Okay. Now, this is not exhaustive list. Okay, so just to be sure, there are lots of other things and lots of other applications of machine learning, but those 4, they summarize perhaps 90% of what we do with machine learning. Now, just to give you some feel of how you approach problems with machine learning, just going to give you some very simple example. Oh, I actually made a mistake here. I called it classification example. In fact, it's going to be regression example. I'm sorry. That's my mistake. All right, so let's say we have this data. Now, what this data is, there are two variables, x1 and x2. These are our inputs, and our output is variable y, and it's vertical axis. Okay, this data somehow distributed. And now our task is, so we have a new observation of input variables. Okay, whatever those values are, just never mind, it can be temperature and the pressure or something, okay, in some standardized form. Okay, so now we have those two values, and we wanted to predict our output y. So how can we go about it if we don't know what the fundamentally is the connection of y with x1 and x2? So the idea, and it's the simplest method, and interestingly enough, it can be easy to prove that statistically it's the most optimal method how you can do it. So this red point here, this is your new observation. The best way you can do is to find observations which you do know, for which you don't know the output, in some neighborhood of the new observation, and take an average of those observations. There are two ways how you can do it. One way, if you say, okay, I'm going to look at the certain distance away from my observation, and that's what depicted here by the orange line. And those methods are called kernel methods. Or you can say, okay, I'm going to might look a little bit further, but I want to include at least 5 observations. In that case, the area would look a little bit, would probably include this extra point here. Okay, and that's called k nearest neighbor. That's probably one of the most common and quite popular and rather simple way of really doing it. Right now, all of that has mathematically strict description of what we're trying to do. So we're trying to find the output as a function of our inputs. We don't know the form of that function, right? And the question is, what form should we use? And statistically, the best way you can do it is to say that it needs to be the expectation, or in this case, it's going to be just basically mean of the output given what the inputs are. And the methods that I describe you basically essentially going to deliver you this. Okay. Now let's see how that performs in our example. Okay. On the plot on the left, we have just the input space, x1 and x2. You see this little red square. This is where our new observation comes in. Now, it's already a bit of a problem here because majority of observations is kind of concentrated here. We would have much better way of estimating the output if we were sampling from here. This is already sort of pushing us to the margins. But nonetheless, there are a few points which are around here. So we can hope. Now, on the right-hand side, now this is a plot of x1 against y and x2 against y. Okay. So now you can see that's where it puts our predicted output. Okay, doesn't look too bad. There is this point here in original observations, which kind of looks like an outlier. But the reason it's there just because it might have fall quite far away in the x2 axis. Okay, so overall that looks reasonable. And similar on x2 against y. Right. I hope everybody followed me on this. I promise that was the most technical part of the whole presentation. Are there any immediate questions? Because that would be very sad if I lose people right at this point.
It looks like everything is clear on our side. No questions yet.
Okay, that's good. Now, just one last comment on this one. So this method works very well if you have a lot of data. The problem is that when you have those variables here, as you can see, x1 and xn, if that n is large, so you have 10, 20, 100 predictors, that space on which you look for the neighborhood becomes extraordinarily large. And calculation of that average, of that expectation from the data that you have becomes essentially infeasible. and that's essentially what sparks the variety of methods that we use. But nonetheless, as I said, this method statistically, that is the best you can do. If you have enough data and your space is not too big, you just should do that. Okay, now let's move to some applications. Perhaps one of the earliest applications of the machine learning methods and the most successful in extractive methodology is application to flotation. It started in middle 1990s even with the work of Derek Mullman, who later on went on and founded the company Stone3. And initially it was essentially image processing, so processing images of the flotation froths and finding your bubble size distribution, finding the what was there, the velocity of the froth, and so on. And as it started in middle 90s, and it moved, and there are more recent research as well. It also changed the methods that it's using. So if earlier it was sort of image segmentation methods, nowadays you can use things like convolutional neural networks. But that remains, to date, that remains the most successful application of machine learning methods. And if you search the literature for machine learning in mineral processing, most of the articles you will find will be about flotation. Now, another application here, now again, it's mineral processing side. That's taken from the article published in 2015, overload detection and semi-autogenous grinding. That is now for milling. Now, since then, there were a few others were published, again, applying different methods, more things like transfer learning and other things. I'm not going to go too deep into that. And again, the idea behind that is that if you have the data that comes from a mill, there's generally quite a lot of observations that are made. And as an operator, you need to make a decision. Are you operating normally or something is going on? And that is the system that helps you to make the decision. And there's a whole bunch of things that needs to happen. How early you can detect it, how sure you can be, are you going to raise the false alarms, and so on and so forth. All right. So these are perhaps the, now with the flotation being the most popular one, on the mineral processing side, it is picking up. Yeah, and especially for the mill grinding. Okay, so now we are moving to things of opportunities, and I just want to highlight like why we're actually doing it. That's perhaps the most important part. And there are a few things that we are looking at. The first one is optimization, and that is usually detection of which mode I'm operating in. This is particularly challenging in extractive industry because essentially you never operate at steady state. Things are changing all the time. The composition of the ore changing, the grind changes. Perhaps it's a little bit more stable downstream, but at the grinding circle, you never operate at steady state. So knowing where you're operating at which mode, and can you move to more optimum mode, that's an important task. Another one is reliability. That comes less on the process itself and more for the equipment. Can you detect the faults that are happening? Can you identify where the fault is? And can you predict whether that fault would develop into complete failure? Because often you can still operate with a fault while you are getting everything ready for the proper maintenance. And finally, it's a health and safety issues as well. Now that comes to reliability. It comes to things like spillages, or what sometimes in some parametallurgical furnaces it's called positive pressure events, which can be rather dangerous. So again, you want to spot those early on. So we have seen that the machine learning being applied for process monitoring. That's perhaps the main application of it. So essentially, we're trying to squeeze an extra bit of optimization out of the process and help with that. Question is, can we find in other areas? That will be very interesting to see. If maybe you have some ideas, it would be very welcome if you can share. Maybe for the process design, who knows? As you can see, what you've seen that was flotation and grinding that were prime applications. Still, there's very little work has been done on hydrometallurgy and pyrometallurgy side. Pyrometallurgy maybe a little bit more. Hydrometallurgy, I really have seen very, very, very little on that one. Right. Now, challenges. Now, this is there are three main challenges that we see. The first of all is data. And that's kind of, I have sort of funny story to tell you. When I joined the pyrometallurgical division, my host was telling me that we want to apply machine learning because we collected a lot of data out of that, which we can apply the machine learning methods. And my question was, now, what is a lot? And in extractive energy industry, if you have a few thousand observations, that's a lot. The trouble is, for machine learning, the volume of the data is, you need to be quite a bit higher. And especially the more advanced methods you want to apply, the volume of the data needs to be higher and higher. Also, how fast you get the data. Right, because at the moment we can accumulate enough data, but that would take us years to do at the current pace. The other thing is what you have in your data, right? So are you measuring what's important or not? And again, it's very challenging in extractive metallurgy in particular, because what you want to measure is a composition of your ore, for example. Or you want to measure, to assign some weight, for instance, of how minerals are disseminated in the ore. But those measurements are hard to do. And again, it comes with the velocity and the volume, how much of the measurements you can do. The another one is a variety. And that the variety perhaps is a problem for all industry, let's call it extractive industry or manufacturing industry, because you try to operate at rather tight, quite tight controls. But effectively, machine learning is such a thing that it wouldn't be able to predict you something that it have never seen before. So it needs to see it. A particular challenge is in application to reliability, because we want to see failures. We want to see equipment failing. But of course, in real industry, you never allow this because that's way too dangerous. And there's going to be people's lives at stake, and it's going to be too costly. And finally is veracity. And that comes, so what you're measuring, is it what you're measuring? Have you checked the sensors on the plant? Are they actually accurate? Have they been checked? Yeah. Now, another part of the challenges of the application is an expertise. And the first one is about training. It's not enough to be a specialist in machine learning and try to get yourself into extractive industry, just because there are lots of things that you need to know about. On the other hand, you also can't just be an engineer and hope that you will be able to quickly pick up the machine learning. So the part of the training that can be really the challenge. In fact, there's two approaches. In my previous postdoc that I did at Stellenbosch University, the sponsor's idea was we want an engineer and we'll train the engineer in the machine learning. At my new place, the philosophy is an opposite. we want someone who knows about machine learning and will teach the person pyramidology. So it can be approached other ways, but nonetheless, the training is important. Another one is the employment part. And that is, where would you find the actual employment? The mining companies, they might not be best employers in that case. And the reason is that they might not afford you if you're an engineer and you know machine learning. They don't necessarily have enough work for you either. And for them, employing you is a problem because you might create a good value, but then you'd probably stay for a few years and you would leave, and there would be no one to pick up your work. And the final one is costs. So all these fancy sensors that we need to collect the data, they cost money. Some of them are rather primitive and maybe it's okay, but others are really, very expensive. And also the mineral processing plants are quite spaced out. So the whole infrastructure, the ICT infrastructure to support those sensors, to keep the data, to record it, and to give it access to whoever needs it, that comes also at a cost. Right, I see there was some comment in the chat. I guess I'm almost at the end of the presentation, so we'll address it when we get there. Okay, and finally about the threats. Now, it was actually quite interesting. There was some, I don't know if you followed it, but there was some questions regarding the ethics and machine learning and ethics at Google, which resulted in some person resigning. But compared to those kind of applications where you have a chatbot that might learn racial or other inappropriate behavior or inappropriate behavior, we're quite not there yet really with our ethics. So it's not directly of machine learning, right? So all we're trying to do, we're trying to operate better. We're trying to operate it more efficiently, and that's win-win for everyone, because when we operate more efficiently, there will be less pollution in the environment. The mining companies will get higher profits. Hopefully, they will disseminate it to people who work there as well. So it's not lying with machine learning itself, but nonetheless, there are areas where it can become an issue. For example, I know that some companies, they're introducing the system that automates the recognition of unsafe behavior or somebody not wearing a PPE. And if it's not trained properly, it might essentially start racially profiling the workers. So we might be aware of that. The future impact, this always comes interesting. So are we essentially cutting jobs or not? Are we changing what the jobs are? Are we creating new jobs? So as for my part, I actually don't know the answer to that yet. How it's actually going to play out. There are just way too many, for me, there are just way too many secondary effects, but that we can discuss. Okay, so, and that brings me to the end of my presentation, and then we can start the discussion.
Hi, Alexey. Thank you so much for that really insightful presentation. We do have a few questions in the Q&A section at the bottom there. Unfortunately, I'm unable to start my video from this side, but I will read out the questions for you. The first question is from Yaku. Good afternoon, Alexey. I've recently submitted a report as part of my studies, and I recommended that a convolutional neural network application be used to monitor the mine's GO-BALT sample to identify variance in the sampling process. Have you ever applied something like this on a belt sampler?
No, I haven't done on a belt sampler. So I haven't done the like the image processing on ores or samplers and whatnot. I did it on slightly different kind of image. I think it's a good idea in general because convolutional neural networks, the way they work, they kind of pick up what we call the now what's the word? So basically, they will be able to detect those edges of where your rocks are. The one thing to be wary of is that you only see what's at the top. So you need to be able to show that what you see at the top has some relevance to what is obscured. I have seen some articles a few years ago on that, so you just might want to look at it. Yeah.
Thanks, Alexey. So we have a question here from Helen Marie. How can the employment challenge be overcome? Such a small little question. Just could you fix that issue? You've only got 20 minutes. Go.
Okay, so one way in terms of the employment. So I'm guessing it's an employment in terms of let me see, where is it? It's this one. The employment here. The one way to do it is you basically won't be employed by the mining company itself. I don't think that would happen. But what would happen eventually is that service would be outsourced to companies like Mintech or Stone3, SAIMM Solutions, what's that other one? I forget the names now. Anyway, those ones. Okay, those who provide highly technical expertise in general. Yeah, I think that's what eventually would happen. But that's my speculation. I can't tell you that that's going to be a solution.
Thanks, Alexey. So we have Katlejo, who says, hi there. I just wanted to find out, where can one obtain a prepared extractive metallurgy data set, any process, online in order to train a model? In this context, which model normally works best, whether it's a regression or a convoluted neural network?
It should be convolutional probably, but anyway. Okay. The data set is a problem in general because the companies don't like to share their data like this, right? But there are a few outlets that you can try. There was a data set that I saw was published last year on what's it called? Kaggle, that competition platform, and that was a flotation data set, as far as I recall. Then just search for Margaret Bauer. She published an article, and also there is a website where there are a few data sets. They're mostly concerned with the controllers, but they are available. That is about it that is available publicly. For the rest, essentially, you need to contact the companies, and depending on their history, depending how well they are in research and how interested they are, they might share the datasets with you. On that note, be prepared that the datasets you're going to receive are going to be extraordinarily messy, and 90% of the time you would spend just cleaning it up and making it in a form that you would actually can use. Now, the second part of the question, which model? So the choice of the model, this is a difficult one. Unfortunately, there is no general rule in machine learning that would tell you, oh, this model will work or this model will not work. You just have to try. But one guideline that I can offer is, if your data set is not big, try a simple model. Okay, the simpler the better. That would be a general idea. Yeah.
Thank you. We have a question from Anonymous. Thank you for your presentation. In your experience and from your vantage point, what is the AI readiness or maturity level in South Africa or even Southern Africa for the adoption of the fourth industrial revolution technologies, such as the machine learning that you speak of? What do you think must happen to change this readiness?
Whoa.
You're getting such easy questions.
Indeed. There's no a single answer to the question. In some ways we're ready, in others we're not. I think the biggest one is from the point of view, we need to show the value in the machine learning. So that's as a researchers who are working in this area. And now in South Africa, in particular, it's actually quite nice because of big platinum industry. Now, platinum is actually a very good target for that because it's such a valuable product. They have tons of measurements done on the plants because it is a valuable product. So there it is possible to find an application. Now, if you move to something like steel making industry, now that becomes a different story, right? Altogether. But the point is that you need to show the value. That's the most important part. And in some cases, we managed to do it, like with the flotation, that was quite early hit. In other cases, we're still struggling. And it's not easy. It's not easy. But the onus is on us on that. I can show, we can discuss, at length, like what's the difference between extractive metallurgy and, let's say, advertising, and why it works so well and was adapted so easily in advertising and not so easy in extractive metallurgy. But essentially, we need to we need to find the value.
Thanks, Alexey. No, I can imagine it's incredibly context dependent, the various problems that we'd face, but it's good to know that at least for me, the first thing that comes to mind when we say machine learning, I'm like, oh my God, I am the product. I am the social product that everyone's going to use to kind of manipulate.
Not in extractive metallurgy, so that's
no, not at all. Yeah, no, I'm safe in this debate. Hey.
Right, so I see Helen Marie is on fire.
Yes. So from Helen Marie, will the large-scale implementation of machine learning slow or speed up our understanding of the fundamentals of mineral processing?
That depends, I guess. That would be the answer. I don't think it's really at odds with the fundamental understanding. And it depends on well, you can also argue how fundamental, maybe the machine learning is a fundamental understanding, really. What is understanding? And so which one you argue is so fundamental. So it comes down to the point of, I guess from machine learning side, is how easily it is generalizable, or is it going to be always only case specific? But again, I don't think it's really at odds. I think it's just different approaches, and they don't even compete. That's the interesting thing. They kind of work very well in parallel, and I don't think that at any point neither industry nor the research will swing one way or another.
Thanks, Alexey. Just sorry, I didn't see Helen Marie did a second comment there saying in referencing fundamentals, I mean fundamental science. I don't know if that changes your answer. Not necessarily.
Well, I mean, the underlying part of machine learning is statistics and probability theory, which is quite fundamental. So depending which science now.
We have a question from Edmund. Does machine learning encompass automation and robotics as well?
I don't think, maybe not encompass, but it's part of those. Yeah, if you want, well, you can do automation and robotics without machine learning, right? But you can do it with machine learning, so it would be part of it. And depending what you're doing, it might be useful or might be not. So that's, yeah, I'm not a specialist, unfortunately, in robotics. Like the last time I was learning about it was about what's now 15 years ago. So it's a little bit hard to say where it is where it is right now. But it is part of it, of course. You know, if you look at the videos from what's it called, the company, Boston Dynamics, I think. I'm pretty sure those robots are machine learning trained.
We've got another question from Cherkaev. Normally, when applying machine learning to an industry database, how accurate are these models in terms of loss and accuracy just in general? Or what would one aim for when establishing a gradient descent? Am I saying that? Yes.
Sorry, just a note to the participants. It would be best if you placed all your questions in the Q&A section, because then I won't miss them. I might not see them if they're in the chat. But in general, I have noted the two in the chat for now.
Okay.
Sorry to hand over.
So now this question, how accurate they are, that depends, all right? So if how successful you can be with your models, they can be quite successful, they can be very inaccurate. The issue, however, is that for lots of things, the industry requires quite high accuracy. So for things to be practically useful, they need to be fairly accurate. Let's say for the fault detection, you don't want to raise too many false alarms, for instance. But you also don't want to miss the fault either. So it comes down to, it's case by case basis. Unfortunately, there's no general answer to that question, and it depends on how strict the requirements are for any particular case.
Thanks, Alexey. A further question. I would kindly like to ask one more technical question from Cherkaev. From your experience or knowledge, in what context has generative adversarial neural networks been used in industry? Can they be applied in hydrometallurgy, extractive metallurgy, in any way?
I have not seen them being practically used. That's not in mineral processing industry at all. The main reason is they require a lot of data to train. That's the general. So in machine learning, you get another sort of dichotomy. You get models called generatives, and you get models called what's it called, discriminative models. Anyway, the generative models would be preferred. Theoretically, they're better, but they do require a lot of data. We just don't have enough of that data. So now, if you still see the slide on the challenges with this 5 V's on the data side, that's where the crux is. Once we get that sorted, then we can start talking about those models. At the moment, we're really looking at very, very simple models that we try to apply. So just give you an example with convolutional neural networks for the image recognition and so on. We generally don't train them ourselves. We take pre-trained convolutional neural networks that were trained to recognize cats and dogs and flowers, and we just use that essentially. Well, there's a few changes that we make, but essentially we don't train them, and that's because we don't have enough data to train them. Yeah.
Thank you so much for your thorough answers. I'm sure they're all very grateful for them. We've got a follow-up question from Yaku. Applying machine learning on spatial data, such as point clouds for predicting possible failures in a mining environment, do you have any input on this? I've started my preparations for my MSc at WITS, and I want to apply machine learning on my current research and development, specifically when it comes to fatal accident investigations.
Interesting. Spatial point clouds. Unfortunately, the question stayed a little bit too vague for me to really give an answer. I have few ideas of what I have seen.
I would
now,
then
generally
suggest what
no,
we could do then is have Yaku step onto the panel if he's willing, and we could go through the rest of the questions if you'd like to get some clarity from him. Then?
Yeah, maybe if you get a little bit more comments, yeah, just to give a little bit more information what exactly he means. Otherwise, I might be answering a completely wrong question.
Okay, Yaku's now on the panel. Will he be willing to come forward and just speak to his question?
Good afternoon. Thank you very much, guys. I really appreciate this. Can you hear me?
Yes, we can hear you perfectly. Thanks.
Okay, so basically what my question entailed is if you use spatial data of, say, an accident scene, and you can actually build a database of historical data of the point clouds, and you can actually go into an environment and scan that again and to look for similarities in a environment where there was a failure, say in a hangwall or a sidewall failure, and actually make a prediction or give a rating based on historical data. That's what I meant with the point cloud data for predicting possible failures in the future.
That's an interesting question. I mean, nothing quite specific comes to my head, to be honest, for those ones, because you can, I mean, of course, you use the historical data, and you can, if you record enough variables, let's say around a certain unit, what we call covariates, and then you can try to predict the failure on the new incoming data from there. But there's nothing really specific that can guide you in that one, because it's just all the methods that it basically doesn't narrow down of the methods that you could apply. That's the issue here. Yeah, it can be one interesting thing. I don't know if it would talk to what you want to see, but there's one interesting method. It's called the causality, where you detect a fault in maybe one part of the plant, and you can try to trace it where actually it has occurred, where it has originated. That may be just one angle of looking at it. Yeah, for the rest, unfortunately, it's a very broad problem that you at the moment that you're looking at. It doesn't really narrow down to the methods.
Alexey and Yaku, there's a comment from the chat from Yelena. Would one not resort to geotechnical data in this case? To be found out in some.
Yeah, that's to be found. Yeah, it's it's very hard to really make. It depends on what kind of data you're looking at. If you look at a spatial variation, yes, you can apply what's so-called kriging, or another name for the Gaussian process regression. But is it going to be something that you want? It might not be appropriate. Yeah. You have to look at the data first, and then you can start looking at what methods you can try to apply.
Thank you so much, Alexey, for your answers. So we've got Just a few more questions for you, and then I'll let you go. We have a question from Sibusiso, which you'll find in the chat. What are the tools you're using for your machine learning, and what variables were you estimating? You also mentioned process monitoring using use case. Can you please provide more details on this point and the outcomes of that work?
Right. Now, in terms of the tools, okay, the mathematical tools basically they're quite statistical in nature. It can be as simple as regression. It can be more complex things like stochastic processes, because most of the time we're actually dealing with time series data. So there is some time structure that is embedded in the data, and if you can uncover that structure, that would be sort of top prize. The kind of variables that we're dealing with, stuff that you generally can measure on the plant, that would be sumps levels, densities of the slurry, well, limited particle size distribution after grinding, flow rates of the pumps, the energy drawn by the pumps, and so on. It depends on which particular unit you will be focusing on. Now, some use cases. So one was looking at reliability of the slurry pump and prediction of the failure if we have detected the fault. That was one example. Short answer to that, it was not a simple task, partially because, again, look at the challenges, look at the data part, and predicting a failure without seeing the real failure on the plant, that was well, practically impossible, if I have to kind of narrow down that. Another one was, for example, prediction of the mode of the mill, again, using some basic measurements around the mill. I'm trying to remember what else was there. Oh, yes, and another one, which is also quite challenging task. So when you have on a plant, certain measurements are done at quite a fast rate, but there are other measurements that can be done quite slowly, and that's your lab assays. But the lab assays are important because that's what sort of drives the plant, right? It tells you what the composition of the ore is, and then it can inform the operator at the flotation plant to how to operate that one. But there is a lag between the lab assays. So the other thing was, can we predict in between the lab assay samples? And again, the answer to that one is it is difficult. Now that one more goes towards what do we have the value in the data? What you're measuring, is it in any way reflection of what you want to get? Yeah.
Thanks, Alexey. We've got a question from Nonyane. What is your view on topographic mapping for fault diagnosis and optimization of metallurgical furnaces? Can it stand the test of time?
I'm going to sound like a very stupid person. I actually don't know what topographic mappings are.
It's self-organizing maps.
Oh, it's those ones. Oh, okay.
Yes, I can tell you because she put it in brackets in the Q&A.
Oh, right, I see it now. Oh, right, okay.
Yes.
My apologies. I mean, look, as I said, there is absolutely no heuristic that can tell you if a particular method will work or fail until you try it. That's the hard part of the machine learning. So self-organizing maps are good tools. They're fairly simple to implement. They don't seem to require such a huge volume of data. So there is a potential there that they would work. So who knows? That people, what I've seen, however, having said this, what I have seen people were toying mostly with support vector machines in that area. But even there, I would say that the application was a bit iffy, to be honest, just the way they did it. So I would try. It's a good method, but I can't tell you if it will work.
Thanks, Alexey. I think Cherkaev would like to thank you so much for all the answers, and I would also like to thank you for all the answers you've been giving, very thorough, well-formed, point by point.
There's another question from Cherkaev.
Yes, there's one last one, and then I will have to close the session. But here we go. I just wanted to find out what is more applicable in extractive metallurgy between TensorFlow and PyTorch. PyTorch, I think. Yes.
Yeah. Yeah. Both of them can work, but you see, with with those tools, which use quite a complex models, you would resort to what we call the transfer learning. So you would take a model that was pre-trained on something else and use parts of it in your application. Whichever one you use, I think it's just a matter of preference. Now, in terms of what I use, I don't know. I use neither, just because there's quite a lack of tractability in those models, and I prefer to stay as simple as I can. If I need, and only get to those complex things when I really have to. But either one of them is just a matter of preference and what is more convenient. So there's not particularly fundamental difference between the two.
Thank you so much, Alexey, for your presentation and giving such insightful answers to all the questions that were posed. I would also like to extend a deep thanks to all of the regular listeners to the MTM online forum for attending throughout the year. I know this has been an incredibly challenging year for most of us, transitioning through to online platforms and just generally working out how to function within a pandemic. So well done us. I think we did well. And I look forward to next year's forums as well. I'd also like to extend a deep thanks to everyone's constant feedback and support. I really do appreciate it. And I would like to invite you as well all to potentially come forward with your own topics and research that you would like to present to the MTM community and the SAIMM community. So thanks to everyone. I hope you have a lovely end of year, and we'll see you all back on this platform next year. Thanks, guys.